In maths, it's very important for us to be able to organise numbers. We use the following notation in order to help organise numbers and sets. So the first symbol says that something is an element of a set. So we could say that 2 is an element of the real number system, which we'll explore a little bit in a moment. The second symbol says it's not an element of. So we can say that the imaginary number I is not an element of the real number system. It is in fact an element of the complex number system, which we don't look at for VCE methods. The next symbol says that something is a subset of another set. So for this we could say that the set of integers is a subset of the real number system. And again, we'll see these sets come up in a moment. The next just says that it is a subset or equal to, so it's just another symbol that you may come across. And the next two are the union and the intersection between sets. So for the first one, it's the union. So something like A union B contains all elements in A or B or both. And we'll see that in a little bit more detail on the next slide. The next symbol is the intersection. So for the intersection between A and B, it contains all elements in both A and B. A and then a dash up here stands for the complement of A, and that will contain all elements in your full set that aren't in A. And we'll see that in action in a moment. The last symbol is a backslash, and it will exclude an element or a set of elements from your set. The union of two sets, A union B, is the set of all elements in A or B or both. So on a Venn diagram, that's all of the blue shaded region shown. And then the intersection of two sets, A intersecting B, is the set of all elements in both A and B. So on a Venn diagram, that's just the overlapping region between the two sets. So we're going to consider the sets A and B. And the first thing we're going to do is we're going to put them into a Venn diagram. So as you can see, 2 is common to both, so it goes in the intersection, as well as 5, which is common to both sets, so it also goes in the intersection. Then 4, 6, 7, and 8 are only in A, so we have 4, 6, 7, and 8 as being only in A, and 3 and 9 as being only in B. So now what we're asked to do is find A intersecting B and A union B. So the intersection of A and B is the overlap. So we're talking about these elements here for A intersecting B. And that is just the set of 2 and 5. So they're the elements that are common to both A and B. For A union B, we're talking about everything that's contained within these two sets. So everything including the intersection. So for that, it's going to be equal to the set of 2, 3, 4, 5, 6, 7, 8, and 9, because they're all the elements that are in the union, or those two circles on the Venn diagram. So the next thing we need to think about is a set, which we're going to just describe as a collection of objects, and often these objects are numbers. That's certainly the case for the video that we're currently doing. The objects contained within a set are known as elements, and the real number system is a set or a collection of all the numbers that you would be most familiar with at the moment. So this R, which is a little bit bold-faced, stands for the real number system. And if we put a little positive superscript on it, we restrict that to being all positive numbers. Similarly, if we put a negative superscript there, we get all the negative real numbers in that system. The real number system contains a set of all rational and irrational numbers. So a rational number is any number that you can express as a fraction of two integers. So a rational number is something like 1/3. And we'll see a few more examples of that in a moment. An irrational number, and here we can see this Q is the symbol for a rational number, so the irrational numbers are the complement of Q, which we give a little dash to, is any number, or the set of all numbers, that cannot be expressed as a fraction of two integers. So an example of this is the square root of 2, which is an irrational number. So here we're going to build up our ideas of the real number system. So the real number system contains many subsets. The first is the rational numbers, which are any numbers that can be expressed as a fraction of two integers, and we'll explore this idea of integers in a moment. So examples of rational numbers include all these that have appeared in this set. So -2, 10, 1/3, 0.12 reoccurring, and that's because this number can in fact be expressed as 4 divided by 33 as a fraction of two integers. -49.6, -0.8, 7/11, -6, and 100 are a few more examples of rational numbers. Then we come across the irrational numbers, so these are going to sit outside the set of rational numbers, and they include things like pi, which we know is a number that goes on and on and on without a pattern, so it's something like 3.14159, etc. E is another number that goes on and on forever without a pattern in its decimal, and you'll come across that a lot in maths methods. Then we have other irrational numbers such as the negative square root of 3 or the square root of 5. So those two are examples of surds. Next we come across integers. So integers are the set of -3, -2, -1, 0, 1, 2, 3, off to infinity and off to negative infinity. Next we have whole numbers, which are essentially positive integers and 0. And then finally we have the natural numbers, which are 1, 2, 3, 4, 5, 6, on and on and on, but non-negative and non-zero. So we'll just do a quick review of inequalities because you should have come across these before. So there's 4 inequality signs. So on our number line shown, we have x is less than a. Then we have the statement x is less than or equal to a, and we can see that on the number line. Then we have x is greater than a, and that's shown on the number line as well. And finally we have x is greater than or equal to a, and that's shown on the number line. Now the thing to note here is that if the dot is coloured in, that is including that value. If the circle is not coloured in, that will exclude the value from the number line. So on the number line, as we've just said, an open circle is used when we have less than or greater than symbols in our statement, and that point is not included on the number line. And when we use a closed circle, which is a filled in dot, that accompanies less than or equal to or greater than or equal to symbols, and that point is included on the number line. We often need to create new sets of numbers that we haven't already described using those bold-faced letters. And to do this, we can use set notation. So this statement here in green says the set of all numbers of x such that, so this little colon here means such that, and we read this as x is any number that is greater than a and less than b. Similarly, we have this set which says that x is any number that is greater than or equal to a and less than or equal to b. Set notation includes the use of the following common sets, which we've already seen. So R is the real number system, Q is the set of all rational numbers, and Z is the set of all integers. We can refine these special sets using a range of symbols. So if we use a plus or minus superscript, we can restrict the set to just positive or negative numbers, and neither of these will include 0. And if we use this U shape, which is the union, we can include another element or set of elements in our set. Finally, we can use a backslash to exclude an element or a set of elements from the set. An alternative to set notation is interval notation, and this can also be used to create new and unique sets of numbers. So here in our green statement we have x is an element of, and this says it's the interval between a and b, but neither are included. So it's x is any number that is greater than a, but less than b. This statement says that x is any number that is greater than or equal to a, but less than or equal to b. So when we express intervals, we use rounded brackets to exclude the number. So that's similar to using the less than or greater than signs in set notation. And we use square brackets to include the number, which is similar to using the less than or equal to signs or greater than or equal to signs in set notation. Intervals like sets can be refined using a range of symbols. So we can use the union, which will include another interval, or we could use the backslash to exclude an interval, but that's rarely used. In general, you'll probably find that interval notation is easier to use than set notation when you're expressing new sets of numbers. So in this example, we're going to go from a number line and then represent those collections of numbers using set and interval notation. So for this one, we have a coloured in dot, which means the number's included. So we go from -20 included to -6 included. So for set notation, we can say it's the set of x such that we go from negative 20 and we say x is greater than or equal to that, but it is less than or equal to negative 6. And these curly brackets just mean that we're talking about sets. If we do the same thing for interval notation, we'd start with x is an element of, and then because the negative 20 is included, we're going to use a square bracket, and then we're going to go all the way to negative 6, and as that's included, we use another square bracket. For b, we go from 12 to 21 and neither included. So for set notation, we'll have x such that, and we go from 12 and we have x is greater than 12 but less than 21. The equivalent interval notation would say that x is an element of, and we'd go from 12 not included, so we use a rounded bracket, up until 21, which is also not included, so we use a rounded bracket. For part C, our set goes from negative 2 included to 4 excluded. So for set notation, we're going to have x such that x is greater than or equal to negative 2. So that greater than or equal sign goes with the coloured in dot, but x is less than 4. So you can see that 4 is not included on the number line, so we don't include it in our set notation. The interval notation for that would be x is an element of, and then we go from negative 2 included, so we have a square bracket, up to 4 excluded, so we have a rounded bracket. For part D, we go all the way from negative infinity, so that's what that little arrow pointing out there forever goes onto, up to negative 2 not included. So we can start off by saying it's x such that we have x is less than but not equal to negative 2, and then we can union that with the next interval or the next collection of numbers, which says that x is greater than or equal to 3 and goes off to infinity. So that's that set there. For your interval notation, you would have x is an element of, and you'd start at negative infinity. And as a really important note, whenever we talk about negative infinity or positive infinity, we always use round brackets. So we go from negative infinity up to negative 2, and that had an open circle, so we use a round bracket to exclude that point. Then we union it with the next interval, which will start at 3 included, so we have a square bracket, up to infinity, and again, whenever we say infinity or negative infinity, we need to use a rounded bracket. So for E, you can see we go from negative infinity all the way through to 0, and now in set notation, we can represent that as all real numbers that are negative. So reals and then a superscript minus says all negative real numbers. For interval notation, we'd say x is an element of negative infinity to 0, not included because it's an open circle. For F, we have 0 included off to infinity. So we can say it's all positive real numbers union with the set of 0. So that's how we can describe it using set notation. And for interval notation, we can say that it is x is an element of 0 included, so we use a square bracket, to infinity, not included, which means it's a rounded bracket. For G, this is just all real numbers, so you go from negative infinity through to infinity. So we can use just the capital R. And for your interval notation, you can say x is an element of negative infinity to infinity, and both of those have a round bracket. The last example is all real numbers, but we're excluding negative 1 because we've got this open dot here. To do that, using set notation, we can say it's all real numbers, and then we can exclude the set of negative 1. And for our interval notation, this is one of the cases where it may be a little bit more tedious to do this, but we can say x is an element of negative infinity all the way up to negative 1, not included, union with negative 1 to infinity. So that's the equivalent interval notation for our number line for part H. So after this video, you should be able to understand the real number system and the special sets contained within it. You should be able to recall and understand notations used to describe sets of numbers. You should be able to use set and interval notation to construct new sets of numbers. You should be able to use appropriate symbols to refine special sets of numbers. And you should be able to interpret a number line and state the collection of numbers using either set or interval notation.